Okay, Rana, turn on your camera. Are you present? Safa, until now I cannot confirm whether you're present or not. Turn on your camera, please, Safa. Great, thank you. Meanwhile, you can write down the topic of today's class is rates of change. Thank you, Hala, for turning your camera on. Rana, only waiting for you. So, Rana, still waiting for you. Hala, Safa, how is your home assignment? Have you tried solving it? Okay, well, what about your home assignment, girls? Have you started it? No? Not yet. So today you're gonna get the new home assignment. So now you're gonna have 3 home assignments. And I strongly recommend you that you don't accumulate those home assignments because I've faced that in the previous groups before you, and every time by the end of the course, everybody's submitting them all at the time. I'm pretty sure you're familiar with it. But mathematics and advanced functions are a specific course because in that case, if you submit all of your home assignments at the very end of the semester, most likely you don't understand what you're writing. Okay? My purpose here is not to make you write endless amount of papers with no purpose. I really want you to learn functions, advanced functions, mathematics, and methods that we are using in this course. Because these methods are used as a base for any advanced studies in any field. Basically, I believe you've heard that mathematics is the mother of science, right? And it's fairly true. And in today's class, we're gonna discover why it is so. And we're gonna talk about rates of change and why I decided to give you this speech, especially today. Because rates of change are all over around us. Let's imagine you're filling up the water in the bathroom, right? You would like to take a bath, and there are gonna be several times that it takes to fill up the bathtub, right? In this scenario, we can give an equation that will describe how amount of water in your bathtub is changing with respect to time. This is a simple example, but it can give you an understanding of what rate of change is. So let's get to pre-required skills real quick, just to make sure that you remember what slope is. Any suggestions? So basically slope, let's say we have 2 points, A and B. And if we join them with a straight line, we draw horizontal line here. This angle would be our slope, basically, right? Like a skiing. When you go for skiing, you have a slope of a hill. And the same one for functions. Functions may also have their own slope. And our studies of rate of change are going to be tightly related to slopes, basically. I hope you're familiar with that, how to determine zeros of standard functions. Basically, to solve them for 0, that's what it means. When left-hand side equals to 0, how to find that value. Make sure to revise that, because it's not part of our class. It's what you were supposed to cover in grade 11. And we're going to start with determining average rate of change. It's important. Right now, write down average rate of change, because there are 2 different rates of change, average and instantaneous. As an example, I can suggest that instantaneous rate of change is when your parents or maybe you driving the car, and on the speedometer you see some current speed, right? You're driving 60 kilometers per hour or 100 kilometers per hour. In that case, you're given with instantaneous rate of change. You also can see that the speed of your car is constantly changing, isn't it? Like you accelerate more, your speed is increasing, you decelerate, speed is decreasing. So the speedometer shows you instantaneous rate of change. Speedometer shows you speed at the current moment of time. It's basically, imagine if you measure something at exact moment you look at it. That's an instantaneous rate of change. Meanwhile, the average rate of change is going to be a little bit different. Now let's see why. We're going to need this definition of an average rate of change. You can write it down right away, this formula. Down here, you're going to use it to calculate rates of change for all the different functions. And what average rate of change is? In a relation, the change in the quantity given by dependent variable delta y divided by the corresponding change in the quantity represented by the independent variable delta x. For a function y equals f of x, the average rate of change in the interval, it's mistake here, it's supposed to say in the interval. In the interval from x1 to x2, right? The average rate of change is going to be equal to the difference in the value of our function in these 2 points to the difference in the coordinates. So let me give you a clear example on how to define this. Let's say we have a graph that represents volume of water that you get in your bathtub with respect to time, okay? Is that clear? And in this graph, let's say this would be 10 liters, This is going to be 20 liters. This is going to be 30 liters, wherever. This is going to be 1 hour, 2 hour, 3 hour. Let's say we're filling up our pool, swimming pool, because bathtub being, you cannot fill up your bathtub for 3 hours, right? It finishes much more quickly. Let's say we're filling up the swimming pool. So let's say my graph looks something like this, right? Here, I injected my water into the swimming pool, and the amount of water is increasing over time. And I am interested in that. How fast am I filling my swimming pool? Let's say from first hour to the third hour. I will use a red pen so you can see it better. From the first hour to the third hour. So I have 2 points in time. And I would like to know how fast am I filling my pool on average. Not at the exact moment, but on average from 1 to 3 hours. How fast am I filling out my pool? So what I'm going to do, I'm going to take my x value in the point number 1. I'm going to take my x value in the point number 2. And that's going to be my difference in x-axis. You see, x2 minus x1. I subtract the beginning from the end. That's my change in x-axis, or change in time. Basically, how much time passed in this interval. Then I look into my y-axis, and I got to look into change from point 1 to point 2. How much more liters I added to my swimming pool in this with respect to this time period. So let's say in this case I added y2 minus y1. I subtract the beginning from the end. y2 and y1 could be also notated as f of x2, or value of the function when x equals x2, and y1 equals f of x1, or value of the function when x equals 1. So now I have my difference in x-axis, or delta x. This symbol can be read as delta, or basically it means difference. And this is going to be my delta y, difference in y-axis. So how do I evaluate my average rate of change? I find a ratio of how my function changes with respect to how my independent variable changes. In this particular example, let's say in 1 hour, I got 10 liters, right? In 2 more hours, I got 30 liters of water. So my delta y over delta x is going to be 30 minus 10, right? Number of liters at the end of this interval and the number of liters at the beginning of this interval. By finding their difference, I find how much more liters I gained within this time. This all divided by x2 minus x1. 3 hours minus 1 hour. I started counting when it passed 1 hour mark, and I finished counting when it passed 3 hours mark. Now I get ratio of 20 liters within 2 hours. So I can say that my average rate of change within these 2 hours was 10 liters per hour. So my rate of change expressed as liters per hour. Do you see the relation here? Kilometers per hour, liters per hour, something changing with respect to the independent variable. You can express any other quantity using this. For example, number of bacteria in the colony. How many bacteria are gained in the colony over hour, right? Or for example, how many planes is the company assembling over a year? You see, your X or independent variable could be time, it could be quantity, it could be anything. For example, let's say I count how many okay, another example. Here we have time in the denominator all the time. What if we don't have time there, but instead this graph will represent number of people with respect to square area, right? Number of people per area. And as area increases, the number of people increases. So this graph, this average rate of change would be number of people with respect to area. As simple as it is. This only depends on the question that is formed in your task. So, is there any questions about average rate of change or about its basically idea of what average rate of change represents? Okay, Hala, I would like to ask you to explain how you understand average rate of change in your own words. Don't worry, there is no wrong answer. We're just discussing together, right? We're just talking about this topic. I would like to see how you understand the average rate of change.
The average rate of change of a function as is a measure of how the function's output values, which is the dependent variable, change with respect of the input value, which is the independent variable.
That's completely right. That's super smart. Good job. So one more time, average rate of change gives us the ratio that represents how dependent variable changes with respect to the independent. Great. I'm gonna clear my drawing. And we're gonna move on to the first particular example that they suggest us here. Goal of today's class is to calculate and interpret the average rate of change on an interval of the independent variable. The following table represents the growth of a bacteria population over a 10-hour period. You see, bacteria are everywhere. And we have certain table of values. When we just started our experiment, there was 850 bacteria. With each hour, number of bacteria was increasing. And we can already say that number of bacteria is not changing constantly. You see, from here to here, from each time interval to the next one, the difference is not the same. For example, from 850 to here, it's how much? It's 272. Here we're gonna get 359. Here we're gonna get 473, etc. You see, the more bacteria there are, the faster the colony growing. Okay. And during which 2-hour interval did the bacteria population grow the fastest? Oh, I gave your answer right now by mistake. You see, what they're looking into, they're looking into difference in the numbers of bacteria within two-hour interval. So from 0 to 2 hours, we don't have really significant growth of bacteria. But from 2 to 4 hours, the growth of bacteria is increasing, as well as from 4 to 6, 6 to 8, and 8 to 10. And in order for us to determine during which 2 hours interval did the bacteria population grow the fastest, we have to use the data of this table and find the difference, basically, or average rate of change for each of these two intervals, right? We could have rate of change from 0 to 2 hours. We could have rate of change from 2 to 4 hours. The only difference are the numbers that we use for our calculations. Remember, we're still using our average rate of change formula, which is here. Numbers of bacteria at the second moment subtract numbers of bacteria at the first moment. And on the bottom, basically difference in a time, how much time passed. We can see that change in time is constant. It's always 2 hours. So it's basically like our interval. We check every 2 hours what's happening there. So what we're doing here, we calculate the average rate of change in the dependent variable bacteria population for each 2 hour interval. Divide the change in the number of bacteria by the corresponding change in time, 2 hours for each interval. Identify the interval with the greatest change in population. So basically what we did, we found the average rate of change for each of these intervals, and predictable that the more bacteria are there, the faster colony grows. And now we prove that. How do we prove that? We say that from 8 to 10 hours, we can observe the greatest increase in numbers of bacteria in the colony. That as simple as that. I don't want to make you write down this table and many unnecessary values. You can take a screenshot of this as a sample. Most important stuff here is this explanation that gives you idea on how to calculate the average rate of change, in case you forget it in the future. Second approach, solution B, would be more practical for us here. In first example, we use table of values, right? Table of values is not always convenient, because imagine if you have millions or hundreds of thousands of values. Are you going to evaluate basically intervals between all of them? No. You would like to work with graph that represents all of these values all together. And in this particular example, what we're going to do, we're going to create a scatter plot using the data from the table of values and draw a second line. It is really important to understand what second line is. Second line is a line that passes through 2 points on the graph of a relation. As here, PQ is a second line. So, the slope of each second line, in this case, remember, slope is the angle between this line and the horizontal axis. The slope of each second line is equivalent to the average rate of change in the number of bacteria over each interval. And it's not a coincidence. I'm going to show you why. From the graph, it appears that the second line with the greatest slope occurs during the last interval from 8 to 10 hours. And it's easy to see that because when we look at the graph, you can clearly differ that here slope is not as steep as it is here, right? Do you agree with me? Here we can see that function increasing much faster than is increasing here. And you may ask me, why average rate of change is somehow related to the slope of the second line between 2 points? Good question. And I'm going to show you that, remember, for average rate of change, we have a formula, delta y over delta x, right? Let's see what this formula gives us on the graph. I will zoom in a little bit more. Let's say I want to look into this interval between these 2 points. So now I have a change in x-axis. This is going to be my delta x, right? Delta x. And I'm going to have my change in y-axis, delta y. Do you agree with me? So now I want to find slope of this line. Slope is going to be this angle. Do you agree with me? Let's call this angle alpha. So I want to find this angle in this triangle. And this is where trigonometry is going to help me. Do you remember the primary trigonometric ratios? Sine, cosine, tangent. This is what we're looking for. We're looking for a tangent. Do you remember what tangent stands for? Tangent stands for tangent alpha is going to be a ratio of the opposite side divided by the adjacent side. Do you see where I'm leading you? Basically, by identifying the average rate of change for any function, we identify the tangent of a second line. Or basically, the tangent of an angle of this second line. This is why average rate of change is related to the angle of this slope. You can write this down. This is fairly important. Let me know once I can move on. Can I clear the desk? Thank you. So, moving on. Now, instead of calculating difference like this, instead of that, we're going to calculate the slope of each second line to verify basically our previous solution. You see here they evaluate the slope of M1. It's going to be a slope between these 2 points, this point and this point. You see moment in time 2 and 0, as well as for all the other points. You can see that as a result, we get the same average rate of change. Again, we can conclude that the greatest change in the bacteria population occurred when the second line is the steepest during the last 2 hours. The bacteria population increased by an average of 412 bacteria per hour in this interval. Safa, I have a question for you. Why is this average rate of change that we calculated right now is positive? And what does it mean? Why is the rate of change is positive? Or you can paraphrase it as, when is your rate of change is positive? Any ideas?
It's always increasing.
Absolutely right. Rate of change would be positive if our function is increasing. This is a good answer. And how is this represented by the second lines on the graph of the data? Let's see here. Basically, same thing that you just answered, the function is increasing. But in terms of second line, you would say that the slope of a second line alpha is a positive. On the other hand, if your slope would be like this, right? If our curve would be decreasing, your angle would be negative, right? So, as well as your average rate of change, your average rate of change would be negative as well. Good. So it is important to remember that rate of change have units, even though slope doesn't have the units. Because when we work with functions, usually dependent and independent variable have their quantity, right? So it is important to remember that rate of change should have some kind of units. In this example, you're gonna see that for any linear function, your average rate of change is gonna be constant over the whole domain of the function. As soon as slope of the second lines in a linear function is the same for any two intervals, you can state that average rate of change is constant for any linear function. No need to spend too much time on this by solving this problem, but basically what you're gonna see here is that no matter which two intervals you take, your rate of change is gonna be the same. It is not the case for exponential, for polynomial functions. For example, bacteria. Usually, growth of bacteria expressed in terms of exponential function, because you can see that the curve for bacteria was like exponent, right? In growing up, and over time keeps growing faster. But for linear functions, average rate of change will be constant. Okay? Same here. They're just using graph to identify points, but all of these approaches end up with usage of the same formula that we covered at the very beginning of the class. F of x2 minus f of x1 divided by x2 minus x1. This is what you have to remember. So, Rana, can I ask you a question? Here, you're asked to calculate the average rate of change in volume during each of the following time intervals, from 30 to 90, from 60 to 90, etc. Could you please calculate the average rate of change from 30 to 90 minutes according to this graph. I'm going to highlight these points. 30 minutes to 90 minutes. This is 90 minutes. Can you calculate the average rate of change between these 2 points? Rana? Rana, are you with us?
Hi. Sorry, I cannot do it because it's really a little bit hard for me. And
Okay, no worries.
when you explain, you should I go back to study again. But I have a problem. I'm not like the same age of those student. I'm a little older, and I study this one back home long time. I have a problem. I need to see the video for you again and again, but I
I
couldn't
see.
find your video.
The videos for this course, they are already on YouTube from past semester, and we're going to upload new videos from this semester soon. I'll fix that for you. And for now, as soon as we can have this nice little discussion, it's not a problem that you may have problems with understanding this material right away. But from my perspective, what you have to do in every class, for example, today we covered this little nice formula for average rate of change. Did you write it down?
Yeah, I understand, but I do it by myself. It's so hard for me. That's why I
Yes.
want to go practice more and more to I can understand. It's really, and sometimes I last time I need to see the more video to understand what's happened. In the class I understand, but if I leave the class, I forget some stuff.
No problem. So here, let me explain you this particular example. Um, in in the question, you're asked to calculate average rate of change between these 2 points. Basically, they're asking you how fast are you draining a hot tub from 30 to 90 minutes, right? Let's say you open the plug in your hot tub and the water is going away. And you would like to know how much water is going out every minute. So between these 2 points from 30 minutes to 90 minutes, I lost from 900 liters, I went all the way down to, let's say, 100 liters. So I got 900 liters at the beginning, and I finished with 100 liters at the end. So using my formula for average rate of change, I can see that on top I have difference in liters, how much liters I lost over this period of time, and on bottom I have difference in time, how much time passed while I was losing these liters of water. So now I substitute my known values into the given formula. F of x2 is our function in the moment of time x2. So moment of time x2 is going to be 90 minutes. And at 90 minutes period of time, I had only 100 liters of water. So it's going to be 100 liters subtract 900 liters that I had at the very beginning of this period of time. Now I have to divide this by time that passed during this period of during this interval. So basically at the end I finished calculating when I had 90 minutes passed, and I started x1 when it was 30 minutes. So basically, I calculated the amount of water that ran away within 1 hour, or 60 minutes. On top, I have difference in liters, which is negative 800, which means 800 liters were drained from my hot tub. And how long does it take to drain 800 liters? It took me exactly 60 minutes to do so. So what I can say that my average rate of change is negative 800 liters per hour. Or if I want to express this quantity in minutes, I would say it's going to be 800 divided by 60. We can subtract 0 here, and it's going to be 1. It's going to be roughly 13.3 liters per minute. Negative 13.3 liters per minute. So this result gives me understanding, first of all, that my function is decreasing, minus here. So water is going away from the hot tub. Secondly, I'm getting a rate of change, first of all, with respect to time in hours. And secondly, I can get the same rate of change with respect to time in minutes. I hope you can understand this example now. Does everybody copy this down? Okay, okay, thank you, Colin. Moving on. This is an example when we have negative rate of change, right? This is how they suggest their solution. Here you can see, oh, look, my approximation was correct, 13.3, nice. So, yeah, basically one more thing to take from here, you can see that if wherever 2 points I connect on this graph, their slope is not the same. You see, these lines, they're not same, but any of this line can represent my average rate of change between 2 points. Because this function is not linear function, as we've seen in previous example. Because of that, my average rate of change is not constant for any 2 points of this graph. Again, until now, we evaluated the average rate of change using the graphs and tables, right? But it's not always the case. Sometimes you may be dealing with certain formula, like here. Here we have a quadratic function. You can see it here. minus 5t squared plus 10t plus 120. Let's read the question. A rock is tossed upward from a cliff that is 120 meters above the water. The height of the rock above the water is modeled by the following formula that we can see, where height is represented with respect to time. Calculate the average rate of change in height during each of the following time intervals. Let's start with that. So how am I going to evaluate the average rate of change for my function from 0 to 1 second? Take a notice that time represented in seconds this time. So let's remember my formula for average rate of change. Delta y over delta x. F(x)(2) minus F(x)(1) divided by x2 minus x1, right? This is the formula I'm gonna use. And what do I need for this formula? I need initial moment of time and final moment of time. Looking into this question, this is already given to me from 0 to 1 second. So x1 would be 0, x2 will be 1, right? So 1 minus 0. For second interval from 1 second to 2 seconds, I'm gonna have x1 equals 1, x2 equals 2, right? And so on. So you can see that the delta x or delta t change in time is constant for any of the 4 intervals. We're basically measuring average rate of change during 1 second, right? That's clear. So now I need to know f(x)(2) and f(x)(1), my values of the function for the given point. How can I do that? Again, I have to look into formula that I'm giving with at the very beginning. Negative 5t squared plus 10t plus 120. It's right here. How do I get f(x)(2) and f(x)(1) using this formula? I simply solve it for x1 and x2. For example, for the first interval, x2 is 1 second, right? So I substitute 1 into this formula instead of t. x1 was 0, so I substitute 0 instead of t into this formula. Let's calculate that together. So for the very first case, 0 to 1, my delta x equals 1, right? 1 minus 0. While delta y is going to be f(x)(2) minus f(x)(1). f(x)(2) equals this function, and moment of time t equals 1. I substitute 1 here, I calculate it, I get negative 5 times 1 squared plus 10 times 1 plus 120, right? So negative 5 plus 10 is positive 5. Altogether gives me 125, right? 125. This is equals to f(x)(2). f(x)(1) when t equals 0. Gonna be same one, but I substitute 0 here. I'm gonna get 0 here, 0 here, and I'm gonna left behind with 120. So f(x)(1) would be 120. Now I can substitute those values into my average rate of change formula. f(x)(2) is 125. Subtract f(x)(1), which is 120, gives me a difference of 5 meters. 5 divided by 1 gives me 5 meters per second. This is my average rate of change from 0 to 1 second. You also can see it down below here. Any questions about this? Any questions about how I did these transformations? Okay. So take a moment to look into this solution, read through these notations, and right now we're going to have a 15 minutes break, after which we're going to continue, and I'll be ready to answer any of your questions, okay? See you at 11:25. Hello, everyone. I'm back with you. Okay. Is there any questions about how to evaluate average rate of change from equation? Because basically this is the most important approach that you have to learn, because rarely you're gonna work with graphs and tables of values. Usually you're just gonna be simply given by formula, and you'll be asked to calculate the average rate of change for this function. Okay. Summary. Key ideas. This is important thing to notice. You can make a screenshot, you can take a picture, you can copy this down, but I strongly recommend you use summary for each chapter that we cover as a support for yourself. For example, later on in some test or whatever, you or home assignment, you face a problem regarding rate of change. What you do? You open the summary of the corresponding unit. Let's review the summary. The key idea is that the average rate of change is the change in the quantity represented by the dependent variable divided by the corresponding change in the quantity represented by the independent variable over certain interval. Algebraically, the average rate of change for any function y equals f of x over the interval from x1 to x2 can be determined as a formula that we wrote down at the very beginning of today's class. Meanwhile, graphically, the average rate of change for any function over a given interval is equivalent to the slope of the second line passing through 2 points, right? We have 2 points, and the slope of the second line is going to give us the average rate of change. Basically, it can be calculated using the same formula. What do you need to know? Average rate of change is expressed using the units of the two quantities that are related to each other. A positive average rate of change indicates that the quantity represented by the dependent variable is increasing on the specified interval, compared with the quantity represented by the independent variable. Graphically, this is indicated by a second line that has a positive slope, or the second line rises from left to right. A negative average rate of change indicates that the quantity represented by the dependent variable is decreasing on the specified interval, compared with the quantity represented by the independent variable. Graphically, this is indicated by a second line that has a negative slope. The second line falls from left to right. All linear relationships have a constant rate of change. Average rate of change calculations over different intervals of the independent variable give the same result, right? This is applicable only for linear dependence or linear functions. Non-linear relationships do not have a constant rate of change. Average rate of change calculations over different intervals of the independent variable give different results. Any questions about the summary of today's class? Okay, take your moment to copy this down, okay? Let me know once you finish, and we'll move on to a few more examples. Move on. Just yes. And let's solve a few more examples and let's call it a day. So let's take a look into question number 7. Here we're dealing with an example where Shelly has a cell phone plan that costs $39 per month and allows her 250 free anytime minutes. Any minutes she uses over the 250 minutes cost 10 cents per minute. So the function, here we have a piecewise function that we covered in the previous class. Piecewise function says that it's going to cost $39 per month anywhere between 0 and 250 minutes. Every following minute that is over 250 minutes is going to cost her extra 10 cents, right? Extra 10 cents per minute. Let's sketch this function. As soon as it's piecewise function, right? It has two intervals which are defined differently. Here we're going to have a cost, and here we're going to have minutes. So first, from 0 to 250 minutes, her cost is constant, right? $39. So just a horizontal line. $39 here. After this moment in time, anywhere after 250 minutes, we're gonna have basically $39 plus 10 cents every minute. Now, I'm gonna add 10 cents every extra minute, right? Basically, my graph will now have a linear dependency, right? This function right here is linear. We don't have any power here. So it's linear function. So starting from this point, my function will start growing like this. Analyzing the average rate of change of this function will tell me that anywhere here, rate of change is 0. Let's show that. Let's take a moment in time. 0 and 250 minutes. Delta y over delta x equals basically y2 minus y1 divided by x2 minus x1. This is going to be equal to y2 and y1 are equal. Both of them $39, right? So it's going to be 39, subtract 39, and on the bottom it's going to be 250, subtract 0. But denominator doesn't really matter already, because my nominator turns into 0, which makes the average rate of change from 0 to 250 minutes 0. And that's logical, because my function is constant on this interval. Meanwhile, in the second interval, I can see that now I have linear dependence. And if I do the same thing for second part of my piecewise function, I'm going to see that my average rate of change is going to be constant anywhere on this interval. And let's go ahead and calculate it. Delta y over delta x. Let's take 2 moments in time, for example, 260 minutes and 280 minutes. I'm going to have 280 subtract 260 divided by sorry. It's going to be 280 minus 260 in the denominator, right? Because these are independent variable, the minutes. And in nominator, I'm gonna have wherever the price at 280 minutes, subtract wherever the price at 260 minutes. How do I calculate that price by using this part of my piecewise function. So for 280 minutes, it's going to be 1/10 times m, which is minutes 280 minus 250, plus flat rate of $39. This would be equal to 0.1 times 30 plus 39, which is equals to $42, right? So that's how much she pays after using 280 minutes of her plan. The second moment on time is 260 minutes. We do the same calculations, but now instead of 280, you're going to do 260 here. Now it's going to be 10 instead of 30 here, or plus $1, and 40 instead of 42 here. So now I know my components in denominator is going to be 42 subtract 40 equals 2 divided by 20, which gives me 0.1. And that's what we were looking to prove. Over 250 minutes, her fee per every minute will be 10 cents. So with every minute, the rate of change basically is 10 cents, right? 1 minute passed plus 10 cents. 1 minute passed plus 10 cents. So my average rate of change for this part of a piecewise function will be constant, and it will be 10 cents per minute. Do you have any questions on this particular problem? Please take a moment to copy down the solution. Okay, you finished copying it down? Yes, no? Everybody, are you still here with me? Yes, yes, great. Great, thank you, Rana. Let's take a look into one more problem. Let's see. These are just practical for calculating the average rate of change. Let's find something interesting here. Not so much to solve here because I would like to keep these problems for you to solve them at home. One second. Okay, let me show you one more solution just to make sure you understand the approach. Here we're gonna solve using the equation, right? Let's say I want to solve the difference, the average rate of change from 2 to 2.01. Why not, right? Here, my interval is getting fairly small, and I will give you a hint for future. This is how we estimate the instantaneous rate of change. Instantaneous rate of change is going to be estimated by making this interval enormously small as possible. But for this case, let's stick with the average rate of change and see what it gives us here. Remember, you always start by writing down the formula for the average rate of change. Your top priority to remember this formula. y2 minus y1 over x2 minus x1 equals to x2 and x1. x2 is going to be 2.01, subtract 2, right? Denominator is done. Now numerator, y2 and y1. I have to substitute 2 in this formula and 2.01 into this formula. We're gonna have 4 times 4, subtract 5 times 4 plus 1 equals 16 minus 20 plus 1. So 17 minus 20 is minus 3. So y1 is going to be minus 3. So I'm going to put plus here because my y1 is negative. And y2 is going to be 2.01 here. Oh, it's going to be 2.01 squared. Let's see how much is that. 2.01 squared is 4.0401 times 4, subtract 5 times 2.01 plus 1. So it's gonna give me times 4. Left hand side is gonna be 16.1604. subtract 20.05 is going to be negative 3.8896 plus 1 plus 1 negative 2.8896. So I'll go ahead and write it down as y2 value, negative 2.8896 over here. Now I have to evaluate my formula for average rate of change. It's going to be negative 2.8896 plus 3. It's equals to 0.1104 divided by 0.01. And we divide this by 0.01. And I get 11.04. Okay, showed you this algorithm one more time. And please keep in mind that you shouldn't be frightened of weird numbers like this one. Make sure to finish your calculations to see if your result makes any sense. And remember that average rate of change, even in small period of time, not necessarily small quantity, right? Because average rate of change gives you ratio of how one quantity changes with respect to another. Okay, that's the all material for today. This is important unit. Is there any questions to me? Any questions at all? Well, thank you for attending the class. I hope you learned something new today. I'm looking forward to see you this Sunday, and I'm gonna post your home assignment today regarding rates of change. Okay? If no questions, we'll finish the class now. Okay, thank you and good luck.